Hi, my name's Alan Roebuck. I'm the president of the Atmospheric Sciences section of AGU, and it's my great pleasure to welcome you to the Bjerknes lecture honoring Jacob Bjerknes, one of the named lecturers of our section. Today the talk will be given by Professor Richard Alley from Penn State University. Richard got his PhD at University of Wisconsin in Madison, my alma mater, great place, and he's the Evan Pugh Professor in the Department of Geosciences. He has a large number of awards, including being an AGU Fellow and a member of the National Academy of Sciences, and wrote a very popular book, The 2 Mile Time Machine, about ice cores in the year 2000. So I'm going to start by presenting him with a certificate, and then we'll have him give his talk.
Thank you, Alan. Thank you to all. Alan is an amazing scientist, has done wonderful things. Those of you who are a little gray-haired like me know this. Those of you who are younger may not know this. To have this size of scientists, of geophysicists here, to look at it, how many brains are here and how much good you're doing, it really makes your heart feel good. We could not have had a room like this when I started coming to these meetings, and it's a testament to the leadership of what they've done here. So you may know I'm not an atmospheric scientist, except by default, and so but I do a history of atmospheric science. And so what I'd like to do is take you on a history tour, and we're going to eventually try to do something with CO2 before we get done. I owe thanks to a whole lot of people, to colleagues who have gotten here, to funding agencies who have really helped me along. AGU, I would note that Professor Bjerknes was an Arctic researcher, among other things, so those of us who like the poles can claim him. He was in the weather forecasting team for the first airborne crossing of the Arctic. And thanks to you, and of course if I screw up, it's my fault. So we'll go with that. And if you've been following the news, if you've been following the blogosphere, I think you probably know that these are interesting times. It is, and I'll show you a slide in just a moment, how many people are interested in our science and would like to understand it. How many people are interested in our science and seem to wish to distort it sometimes. And I'll show you an example of that in a moment. So with my title up here, The Biggest Control Knob, let's be very, very clear. We cannot fire either the climatologists or the meteorologists once we know that CO2 makes it warmer. This is not the answer to everything. It tells us nothing really exciting about regional climates. It tells us nothing really exciting about ENSO and a bunch of other things. So there are more things than CO2 that matter. Studying them is wise. They should be in what we do as we go forward. So as I focus on CO2, remember I'm looking at this through the lens of a historian. And I think what you'll find is that by doing that, it turns out to be fairly useful. Now, this is where I said these are interesting times. Okay? This is a copy of an email that was sent to my administration by an alum. And said alum copied me on this, so I believe I am fair. The alum asked for certain personnel changes to be made, and I have just put in the ones that relate to me. So, so for what it's worth, Dr. Alley's work on CO2 levels in ice cores. Now, I don't actually do that, but I talk about it. Okay, Dr. Alley's work about CO2 levels in ice cores has confirmed that CO2 lags Earth's temperature. This one scientific fact alone proves that CO2 is not the cause of the recent warming. I continue to mislead the scientific community. There should be prompt response, getting rid of me. I have crimes against the scientific community, Penn State, the citizens of this great country, and the citizens of the world that must be dealt with severely because of my shameful activities. Okay. So there'll be a wanted poster up here somewhere. But the thing which is fascinating, and we'll come back to, is that this email has in it a logical fallacy which is evident on casual observation. And I think it's worth our understanding at some level how polarized the world is, how easy it is for someone to misunderstand our science if they aren't fully within it, the amount of education, the amount of outreach, the amount of clarification that we have to make to get from this to a proper scientific understanding. And this is a real job because this is not quite there yet. Okay, so at any rate, I teach a history of the Earth's climate. We have meteorologists come over, geographers come over, and geologists get in. I used to teach this from my science, abrupt climate change and the Younger Dryas and disasters, and it didn't work very well because that's only a little piece of the story. But this is a class in geology, and we were looking at deep time. And what we've come to after a while is the realization that this should be taught most easily from the broad history of the globe's climate, and that when we try to teach that, CO2 keeps inserting itself everywhere we look. And that really, if you leave CO2 out, nothing makes sense. If you put CO2 in, a whole lot of it makes sense, and then you can put the other pieces into the puzzle and make it work. And so what we're going to do is wander through the history of the Earth's climate and sort of see how CO2 keeps being the only explanation for a lot of what happened, which is validated, which works. And so that's my purpose here, is we're going to walk you through 4.6 billion years of history, all the way up to the present, and we're going to start at the beginning and see where we end up. The beginning, as you probably know, the sun is up there burning hydrogen to helium. Helium is denser, its gravity is stronger, it makes the sun burn hotter. And so the sun's output is calculated to be increasing over time. We have no direct observation of solar output 4.4 billion years ago, but the solar physicists are clear on this. It's coming up. If you try to keep the liquid water on the surface of the Earth with 70% of modern sunshine, if you try to do that by changing the Earth's albedo so we soak up more sun, it has to be perfectly black. And a perfectly black Earth is not going to work. And so in point of fact, what we do is we know from geologic evidence that there is liquid water way back. And that in turn means we have to have a stronger greenhouse. Now there's a whole bunch of people have looked and said, so what could have been doing this? Is it methane? What's the methane do in the upper atmosphere with clouds? Is it something else? Is it something else? So far, there's a whole bunch of people still trying to find more greenhouses. They may succeed. But so far, the only thing that really works is one that came out of work of my colleague Jim Casting and others, which is this CO2 rock weathering thermostat. It is a beautiful, simple thermostat. Volcanoes put out CO2 and volcanoes put out rock. And the rate at which volcanoes put out CO2 and rock has very little to do with the surface temperature. The recombination of the CO2 and rock, we call rock weathering. It goes on, it's going on out there right now. And that's a chemical reaction which is thermally activated. And if you turn up the temperature, the recombination of the CO2 with the rock goes faster, but that draws down CO2, and then eventually it ends up in the ocean, and it goes out into the subduction zone, and it comes back out. But this piece doesn't care about the temperature of the air, and this piece does, and now it's a thermostat. Turn up the temperature, CO2 is drawn down, and that cools. Turn down the temperature, CO2 builds up, and that warms. And this one, it turns out, if you put it in models, it is sufficient to explain what happened. And so far, we can't find anything else that is. Okay, our physical chemical understanding says that this is working. We don't have sort of pound on the table, this is nailed, we're done on this one yet. But the best explanation is that this CO2 thermometer, the thermostat, is what has kept us with life in liquid water for 4 billion years. There's a very interesting thing comes out of this, which is if this is correct, if CO2 is regulating the really long-term behavior of the planet, can we demonstrate it? Is there anything that would demonstrate it? And it turns out there is. Because the CO2 thermostat takes 500,000 years or so to work, which means that it's possible to get fairly large fluctuations in temperature before this thermostat brings it back. And in particular, we have these, all our students have big fights about who gets to talk about Snowball Earth because it's way coolest. And so, in point of fact, the Snowball Earths demonstrate that this thermostat really is working with moderately high confidence. As you probably know, and I'll show you a picture in just a minute, there are certain intervals in Earth's history when we have low-latitude glaciation. You look at, a compass needle plunges at the poles, and it's sort of horizontal at the equator. Well, you've got compass needles frozen in the rocks, and they tell us that there's glacial deposits at sea level interleaved with marine deposits near the equator as well as near the poles at certain times. That is indeed possible even with the thermostat, because if you turn down the temperature fast, you can make it cold. And if you make it cold and you get a lot of ice down near the equator where it's reflective, it gets really hard to get warm again. And you would build up a lot of volcanic CO2. And then when it got warm, all that CO2 would break down rocks like crazy. And it would dump in the ocean, and you should have huge amounts of deposits of rock made of carbon dioxide and other things at the end of a snowball. And so there's sort of a prediction here. If CO2 is our key to these deep time things, then sitting on top of the snowball, you ought to find the CO2 turned to rock by breaking down the rocks. And so what do you do? First of all, these maps, the little stars, the different colors are different rock types, but basically the little stars are where there are glacial deposits at certain times, and the equator runs across the middle in all of these, and you'll see stars on the equator and stars far away from the equator, so there's certain times it got really cold. Okay, and the data are pretty good. This is the kind of thing it looks like. Paul Hoffman here, these are drop stones from icebergs in a marine deposit, and on top is the capped carbonate. There's the CO2. It breaks down the rocks, it puts the material for carbonate rock into the ocean, it precipitates in the ocean, and there it sits. And all of the snowball Earths, where the glacier did it, have sitting on top of them the CO2 that built up and broke down the rocks. So it really does look like this is sort of going on. We don't have really good paleo CO2 barometers this old, but it sure looks like it's what's going on. So as we come younger, we get the ability to tell how much CO2 is in the air. Okay, so CO2 paleobarometers, I'm going to do about 2 or 3 slides on what these are. How do we know CO2 in the past? Okay, our gold standard is the ice cores. You drill an ice core, you break the bubbles, you suck the CO2 out, and you measure the concentration. Okay? We've only got about 800,000 years. There's a big effort trying to find million-year-plus ice that may yet succeed. We've only got one core that actually goes that far, and so duplication is back only, 400,000 or 500,000 years, something like that. But when you get younger than that, then there's lots of records, and they duplicate each other very well. This works. If you take the youngest samples that have just been made in the places where it snows like crazy, they match the instrumental record. If you measure the gases in the fern, in the snow turning to ice, it matches beautifully with the instrumental record. If you go to different places in Antarctica, different snowfall rate, different temperature, different impurity loadings, you get the same record. That cannot be an accident that depends on the impurity loading if the different cores with different impurity loadings, different temperatures, and different snowfall rates gives the same answer. And so we have high confidence that the ice core record really is good. Furthermore, we know how to break it. If you go to Greenland, there are places that you do get melt, and when the meltwater trickles into the snow and refreezes, it traps excess CO2. And you find that excess CO2 in the refrozen meltwater, but it isn't smeared out by diffusion. It isn't trickling down into other ice. It's right where it was. And so the good ice is really good, and a good CO2 record from an ice core is a CO2 record. Now, when you get older than ice, this gets hard, because there's nothing directly that is writing down the CO2 concentration. What it is the CO2 concentration is controlling something, and that something is being recorded in the geologic record. And so what you do then is that there are uncertainties. We probably will never get to the point of saying absolutely positively this one indicator gives you the CO2 history. However, there's several techniques, and there's really good people working on the different techniques, and the assumptions that go into them are largely independent. And so when the different techniques agree, then we can have pretty good confidence that we actually are watching the CO2 history of the planet. So what are the techniques? One of them is basically if you were a plant, you use the fast-diffusing, easily reactive light isotope, carbon-12, if there's plenty of CO2. And if you don't have much CO2, you have to use the heavy stuff because that's all that's left. And so the ratio of heavy to light carbon in a plant is a measure of the availability of the CO2 for that plant. The places that we usually find remains of plant that are useful for reconstructing this are particular really tough molecules from cell walls of bugs that live in the ocean that can go right through the gut of a worm without being broken down, or the carbonates in the soil that got their carbon from the air ultimately, or things that grow in fresh water that don't fractionate too much against CO2. And so all of these different things are ultimately telling you about CO2 abundance in the plant's environment. If you go in the ocean, the places that there aren't huge numbers of plants growing so that CO2 is drawn down by the plant growth, then that's a pretty good measure of what's in the air. Okay, now a different suite of indicators. There is boron in the ocean, and the boron comes as BOH3 or the charged BOH4 minus, and you can see with that OH in there that the fractionation between these is going to depend on the pH of the ocean, which listens to CO2. You crank up CO2, you put more H plus in the ocean, the H plus grabs off the OHs from there, and you make more of this stuff. Well, it turns out this is the one that goes into carbonate shells of little critters growing in the ocean, and so you can get an idea of the ratio of these from how abundant that is in the shells. And it also turns out that the boron isotopes fractionate between these, and so you can get an idea of the pH of the ocean from the isotopes as well as from the amount of boron that goes in. And then you do something completely different. If you're a plant, you breathe through stomata in the lower side of your leaves, and you also lose water through that. And so if you're a land plant, if you do too much breathing, you lose water and you dry up and die. And so you want to get enough CO2 to live, but you don't want to dry out. And so if you're grown in a high CO2 environment, you don't make many pores to breathe through. And if you're in a low CO2 environment, you got to have the CO2, so you make a bunch of them. So the number of stomata in the bottom of a fossil leaf is a tracer of CO2 in the atmosphere. And then there's a variety of things that sort of, if you're making fossil fuel, you're taking CO2 out of the air. If you're burning fossil fuel, you're putting it back. If there's more volcanoes, there's more CO2. So Bob Berner and colleagues have been working for a long time to use the geologic record through models to understand the history of CO2. So there's a whole bunch of different paths here. And they work pretty well. Not perfect, but pretty well. Now, if we're going to do paleo-CO2 barometer, what might change CO2 in the past? And here's the broad outline. If you have more volcanoes, they put out more CO2. If you feed more shells into the volcanoes to melt, they put out more CO2. If you have less rock weathering, the CO2 stays up there. So if everything is flat and there's huge thick layers of soil, then the atmospheric CO2 can't get down to beat up the rocks, and so the CO2 tends to stay in the air. And then there's the fossil fuel terms. So essentially it's the weatherability of the surface, how much is coming out of volcanoes, and what we're doing with organic carbon are what control CO2 over geologic time. So I hope you can sort of get the idea that, you know, if there's a mountain range, the soil falls off of it and the CO2 can get to the rocks, and you make mountain ranges in continental drift, and that takes 50 million years or 100 million years. And so you're going to see big changes in CO2 over long times as you tweak these things. Evolution, when you get land plants, it changes. You can now make coal. If you don't have land plants, you can't make coal. If you can make coal, you can bury organic carbon. So evolution is going to affect carbon over long times, and mountain building and plate tectonics or drifting are going to affect CO2. So here's a story, very nice story. The data are on here. 400 million years ago is on your left, today is on your right. Various reconstructions of CO2 from indicators are shown by the different colored curves down here. The model band coming from the Geocarb 2, which is an offspring of BLAG, is shown in the green shading. A lot of uncertainty, but you'll see certain patterns which are rather nicely preserved in here, and a fair amount of agreement. Hanging down from the top is how close to the equator ice was getting. No ice to speak of, ice getting pretty close to the equator. No ice to speak of, ice getting pretty close to the equator, halfway down, sort of. So there's 45 degrees right there. Okay, what you might notice is that these hang down in the low spots here. When CO2 is low, we have ice. When CO2 is high, we don't have ice. Thus far, we have not found any possible way to explain this that does not involve some level of causation. The CO2 makes it warmer, and the warmth melts the ice. And this sort of works, and you just see it right there. When I was a student, this was a problem, and it turns out that there actually is a drop in CO2 right there. Work by Lee Kump and others is showing that. I'll come back to that later. But broad picture is CO2, temperature, you know they're going with each other. And the next slide, I'm going to focus in on this one. This is not a complete CO2 story, but if you haven't heard this story, it's just truly amazing. You gotta hear this story. Right, 251 million years ago, basically almost every critter on the planet dies. There's a great dying, the end Permian extinction. Maybe 95% of the species go, but because you can keep a species alive with a reasonably small number of individuals, this is really nasty. Okay, and it turns out that there are bugs in the ocean, green sulfur bacteria, that use hydrogen sulfide rather than water in their photosynthesis. And they have very interesting biomarkers. And those biomarkers are found widespread at the time of the dying. Which means, and these things are living in the photic zone of the ocean, and they're living on hydrogen sulfide, which means that the ocean's surface is full of hydrogen sulfide. And if you breathe very much hydrogen sulfide, you die. And it's probable that that was true for a whole lot of oxygen-breathing critters back in the past. And so sometime here, the ocean gets full of hydrogen, it runs out of oxygen, and then it gets euxinic, and it fills up with hydrogen sulfide, and then it kills off most stuff on the planet. And it turns out that that happens to be a warm time. There's a big warming coming up to that. And the warming seems to have been because there was a big volcanism. Most of the time, volcanism sort of behaves itself. It has time variations that are very important and that Alan Robock works on and recreating that history. But the mantle down there is, if you could see the mantle sort of sped up a few million times, it would look like convection clouds. You know, you get these big rising plumes of things. And if you try to shove a rising plume up, the top sort of gets blunt sometimes. You get a mushroom cloud. And if you start a new plume, then that mushroom cloud hits the surface. You get lots of lava, lots of volcanism. And the Siberian traps are right at this time, and they're the biggest volcanic outpouring of this entire interval. And so you make it hot, and when it's hot, it's hard to get much oxygen in the ocean, and you crank out CO2 like crazy, and you crank out rocks that the CO2 can beat up, but the CO2 is coming out so fast that you can't pull it down, and you just fertilize the crap out of the ocean, and the bugs grow, and the bugs die, and they sink, and they use up the oxygen, and then all heck goes. And this is far more than a CO2 story. It's far more than a warmth story. But when the ocean's cold, it's really hard to run it out of oxygen, and when the ocean's warm, it's a lot easier. This is fairly simple physics. And so, once again, there's a warmth here. There's a warmth that's attributed to CO2. We can't figure out how else to get it. And that, combined with some other things, gives you a very interesting event. Okay. Now, come a little farther forward in time. We're now in the Saurian sauna of the mid-Cretaceous. It's still hot. There's no ice near sea level at the poles anywhere. You have balmy temperatures. You have forests crowding up to the edge of the Arctic Ocean. The continents are not that different from now. And if you put them in a model, as has been done, you know, you melt all the ice and the sea level gets a little higher, and that changes the planet's albedo a little, and you get a little bit of warming, and you move the currents around, and you might a little bit of warming with some configurations. You can't get much. And so it's really stinking hot, and the only explanation we can find on this is that CO2 is really high again. And probably, again, because volcanism is running pretty fast. If you put high CO2 in the models, you sort of match what happened, except the world seems a little bit too warm at the poles. If you leave the CO2 out of the models, you don't get very close. The only way we can attribute this warmth of having an ice-free world is to have a high CO2. These are some data on that. Over here on the left, this is from Karen Bice's work and others. Over here on the left, this is a temperature scale in degrees Celsius for a site, Demerara Rise, down in the Atlantic Ocean at 9 North. And today, temperatures are down here. And in the Cretaceous, the Saurian sauna, the temperatures are up here about 37 or a little, maybe 38, something like that Celsius. That's pretty hot for an ocean temperature. Even if it's a little bit restricted, you start cranking up to 37, and that's hot. CO2 reconstructions were over here. Before us, it was at this level, and we've raised it to about this level. And back then, it was about this level. Depending on how much fossil fuel there is, we might get to this level and we might get a little above this as we run into the future, which is worth thinking about because that's quite a warming. Whether we'll get that or not is an interesting question. But at any rate, high CO2, high temperatures. We can't explain them without them being causal, okay? That was right in here, the Saurian sauna and this warm time in here, no ice. Now we're going to focus over here as we're cooling towards the ice. There's one more little blip that we need to look at right in here, and then we'll slide down into the Ice Age world. That little blip, so here we are, the dinosaurs die here. CO2 did not kill the dinosaurs, the meteorite did. It has nothing to do with CO2, okay? There is more than CO2 in the world. The dinosaurs die right here, and, but we can't find many other big meteorites, okay? And then there's some interesting little blips along here, and we're going to look at this little blip right there. And that's a very interesting little blip. It's where the Pliocene meets the Eocene, and it is a thermal maximum. So we call it the Pliocene-Eocene thermal maximum. Geologists are fairly literal sometimes. Okay, what do we find there? There's a big isotopic anomaly that it says CO2, CO2, CO2. Maybe starting as methane, but going to CO2, okay? There's a big temperature change. The whole world is already hot, and it cranks up a few degrees C in a fairly short order. The ocean acidifies, and all the shells on the seafloor are dissolving, and there's a big extinction event of things that live on the seafloor. Pretty much all the ecosystems get kicked around. There's huge migrations. There seems to be the start of some evolution going on. There's a lot of ecosystem disruption. Things get out of place and out of time, as it were. You can't possibly blame this on drifting continents. It rises in a few thousand years, and it falls in a few tens of thousands, 100,000 years. So this is not a drifting continent thing. The CO2 shows up, and it gets hot. And it's fast compared to other things, and the way that it recovers looks just like our carbon cycle models. It's beautiful. It really does. Here it is. These are ocean sediment cores, and most ocean sediment core, if somebody drilled the ocean sediment core, they're looking for dead bug shells to analyze to do paleoclimatology, and then the core is usually sort of whitish because it's full of these foram shells that have carbonate in them. And if you come up here, it's sort of white, and it turns dark. And there you can see the drop in carbonate content, and then over 100,000 years, it turns white again. And this is, the shells on the seafloor were dissolved, and there's no new ones getting to the seafloor. The ocean has gone acidic really strongly, and even at fairly shallow depths, that's 2,700 meters, and this is as you go deeper. So right there is the event. The ocean is acidic, and that has an extinction event with it. If you turn that on its side, here we are from 56 to 54 million years ago, and here we go, and there's the CO2. That's the signal of the CO2 kicking the isotopes of carbon. Boom, and it comes back. And here's the signal of the temperature. Boom, and it comes back. The CO2 went up, and this is up in CO2 world. The CO2 went up, and it got warm. And there you see them running together with each other. If you do it on land, this is just the signal of the CO2, not the temperature. But if you do it on land, this is in carbonate nodules in the soil, and this is in teeth. It doesn't matter what you measure. You can line everything up now based on this CO2 release and the isotope excursion from it. This is where Carano et al., Peter Wilf at Penn State is in on this. this is leaf damage in fossil leaves, and the leaf damage goes through the roof at this time. You've sort of messed with the ecosystems and something weird is happening. So these are burrows in fossil leaves. Look at that. That one's been eaten away, and here's somebody crawling around in there eating their way through. It's really amazing stuff. Okay, so we keep looking at this, and we go really deep and we go shallow in time, and all we find is that temperature sort of looks like CO2, and we don't find any other way to explain this, okay? Now, when I started doing this, when I was learning this as a student and as a young professor, there were a bunch of places that we'd point at and say, oh, but there was a big global change and CO2 didn't go with it. And in the time I've been in this field watching, almost all of those have disappeared. So the Ordovician, we thought, well, there was glaciation when CO2 was high, and then you sort of refine the sampling, and look, there's a drop in CO2 at the glaciation. And for a long time, there was this interest that apparently the Cretaceous, the Saurian sauna, the tropics weren't very warm. And the poles were, but the tropics weren't. You got CO2 high, the poles get hot, but the tropics don't. Why not? Because the shells had been changed and they weren't really recording the temperature. And if you find the shells that are buried in the mud and are really, really hard to find, but you get some poor grad student who finds them, you find it was really stinking hot. And so the problem disappears. I'm going to show you the next one. This one we're not done with yet. But 2 years ago, I would have said, well, something goes wrong in the Miocene. 10, 15 million years ago, this doesn't work. We don't know why. And now I'd say, well, maybe it does. And so here we go. So what we're going to do, we're coming through temperature dropping to the present from the end of the dinosaurs to today on your right. Various estimates of CO2, they have a lot of range, and we're going to go right to this low spot in the estimates there. This is 2007, and since then, that looks like it's going to pull up and it's going to match the temperature. So here we go. We're going to do the next slide is this little interval right here. And what do we find? The green curve is temperature from 25 million years ago to 10 million years ago, cooling along here. 2 years ago, what was available to us were these estimates of CO2 from two techniques that don't totally agree with each other, that get really low values, and that don't match the temperature. And we just said, wow, we've got troubles here. 2008, a new indicator is brought on, and you know, those sort of track the temperature. And that's the yellow with the black circles sort of looks like the temperature. So now we've got a disagreement. Tracks, doesn't track. Well, last week or the week before, we get this great paper by Tripodi et al. Temperature is now on the bottom down here and CO2 on the top. I'm sorry I didn't have time to get these replotted. But so here's temperature and here's CO2, and they again are tracking each other. And I'm going to just graft some plots together. Green is the temperature history. You see just faintly in there the old measurements that didn't match, and then the new ones and the new ones, and they agree with each other pretty nicely. Now, this one, we don't know, because this is good science and this is good science. So we're not sure. There's still some uncertainties floating around in there. But 2 years ago, I would have said, wow, we've got a big global temperature change and it's not CO2. And more data, it sort of tracks the CO2 again. And so the anomalies are disappearing fairly rapidly. And there aren't a lot. I can't sort of think right now what I would point at and say, wow, there the temperature did something big without CO2. Okay? And that most recent indicator actually tracks the ice cores very well. So that's something that's worth noting. Okay. Now, we're going to do the ice cores here briefly. This is the one that I'm supposed to be fired for. You'll remember that CO2 goes up and down, temperature goes up and down, and they sort of look like each other. But we know that the CO2 is not causing that. This is a fast Fourier transform of the temperature, and you'll notice that there's a peak here, and there's a peak here, and there's a couple peaks down here. And the position of those peaks was predicted 50 years before it was observed. And the predictions were this arrow from the eccentricity of the Earth's orbit, this arrow from the obliquity of the Earth's orbit, and these arrows from the precession of the Earth's orbit. There's no doubt that that the ice ages are paced by the orbits. There's no way that the orbit knows to dial up CO2 and say change. The orbit has to change the ice sheets and other things that then have to change the CO2. And so it shouldn't be terribly surprising if the CO2 goes a little bit behind. Now remember, the argument against me, CO2 lags Earth's temperature. This one scientific fact alone proves that CO2 is not the cause of the recent warming. Okay? In case, first of all, don't blame Penn State. I don't know what went wrong this time, but we do a good job. Okay? And in case you ever run into this one, and I have heard this one from important people in government as well, let me do something for you here that may prove useful if you have to discuss this out in public. There's no question CO2 and temperature have changed essentially together. The data are good. And there's not much doubt that at times the CO2 is a little bit behind the temperature by a few centuries. The temperature never goes very far without the CO2. The CO2 never goes very far without the temperature, but they're not perfectly together. Okay? So what I want you to do is think for a minute. I go out with my credit card and I'm doing Christmas shopping and I go into debt. Right? I overspend and I'm in debt. And so my credit card company is gleeful because now they can collect interest payments, and I go deeper into debt. Now, remember that interest lags debt. Now, this correspondent to my administration has said that because CO2 lags temperature, there is no possibility that CO2 can contribute to temperature. By the same brilliant logic, interest lags debt, so I never have to worry about the credit card company. They never can damage me. It's wonderful. Okay, right? Okay. Now, but you might ask the question: how do we know that interest contributes to debt? Well, first of all, if you try to, you go fundamentals of economics or bookkeeping, and they say, well, if I give money to the bank, they have my money. And if I don't have the money to begin with, I'm deeper in debt. And then you go and you try to build a little numerical model in your Excel spreadsheet, and you see if interest explains the debt, and it does. Right? So then you do this for climate, and we know that the orbits drive the warming that causes the CO2 rise, it causes more warming. The CO2 is lagging the warming. How do we know CO2 adds to the warming? Well, it's physics. And if we implement that physics in a climate model, it is necessary and sufficient to explain the warming. And let me walk through that a little bit here. Okay, so the ice ages are orbitally paced. There's virtually no globally average change in forcing. And yet there's a globally average response of 5 to 6 Celsius. Okay? What we find is when you turn down the sun in Canada in the summer, you grow ice. And the ice is reflective, and the ice grinds up rocks to make dust, and the ice changes the vegetation. Those affect the planetary albedo. And if you take a good climate model and you put in the maximum ice and the maximum dust and the maximum vegetation changes, you get about half of this cooling. And that's cheating, because you can't get the ice and the vegetation without changing the CO2 in the model. But at any rate, you only get about half. If you put in the greenhouse gases, and especially the CO2, you get the other half. And it actually agrees pretty nicely. And so this is the same as my bookkeeper that I don't have, trying to explain my debt to the credit card corporation. You look at the fundamentals, and then you look at a numerical implementation of the fundamentals and see if it quantitatively explains what happened. And we can't explain this without this. Okay. So why the CO2 changed, I had a bunch of slides that I took out because we're going to run out of time, but we're still working on that. Basically, I don't know if Wally's around, but for a number of years, Wally Broecker used to generate new hypotheses for the CO2, and as usual, he was right. And he put out several of them, and probably several of them actually contributed when all is said and done. The most interesting one now, and the one I think people think really was most important, as you know, things live in the surface water. They turn CO2 into plant. Plant gets eaten by animal. The animal dies and it sinks, or it poops and it sinks. And that CO2, the organic stuff, gets burned in the deep ocean and releases CO2. Burned in plants and bacteria and what have you. So life is putting CO2 in the deep ocean. If you put it down faster or you bring it back slower, you raise CO2 in the deep ocean at the expense of the atmosphere. And if you put more sea ice or you stratify the Southern Ocean, you tend to trap the CO2. And it looks like that is a piece of the story. It's down there. Okay. So I hope I've convinced you as we walk through the history of the planet that CO2 is necessary and sufficient to explain most or all of the big temperature changes of the globe. Okay? Now, is there anything else that we should be worried about? Yeah, the meteorite did kill the dinosaurs, but there aren't many big ones that were down there. We don't have a long record of the sun. I wish we did, but we don't. Okay? But I'm going to give you sort of a sketch. We will never kill all the hypotheses. There's always another bright idea out there, and it may matter. But a whole bunch of the competing hypotheses don't work. Okay? So volcanoes, we know this is the last 1,000 years of temperature in the gray bands, and then the models are on top. And this is the big volcanoes. This is Alan Robock's work. So this is the big volcanoes that cool. And here's a couple of estimates of the sun. The brown one is probably the better one, and the blue is sort of as much as is possible. And what you find, for example, when there's a bunch of big volcanoes, they make it cool. In addition, if you really take this apart, you will find that when the sun changes, it does seem to show up in the temperature record. It is very reassuring that if you change the sun, the temperature notices. And it is very reassuring that as far back as we can see well, the sun is friendly. It just doesn't change very much. If the sun changed a lot, it would control things hugely. But it only changes really slowly or really small as far as we can tell. The records aren't as good as we'd like. There's work to be done here. But it just doesn't seem to be doing much. The volcanoes, there might be a little organization of volcanoes. We know that they matter. This is a stack from the GISP-2 ice core. And when there's a big volcano, it makes it cold. And that's the cooling from a stack of a bunch of volcanoes. And if they could get organized, they'd rule the world. And there might be a tiny bit of organization with flexing of the crust and loading and unloading on ice age cycles, but they're not very organized. There's no good way today for a volcano in Indonesia to tell a volcano in Alaska it's time to erupt. And so they matter hugely, and their clustering gives us a lot of these fluctuations in temperature, but they're not controlling the world here. You know, it's just, this one is important to carry home. People say, oh, wait a minute, the sun doesn't change much, but the sun modulates the cosmic rays modulate the clouds modulate the temperature, and so the sun is amplified hugely. It's really interesting hypothesis. There's really good science to be done on this, but we have reason to think it's a fine-tuning knob. Because this record, this is 60,000 years ago on the left up to today, and this is a record that is beryllium-10 in the ice core, and the beryllium-10 is made by cosmic rays. Now, the sun modulates cosmic rays, so do the magnetic field. And 40,000 years ago, the magnetic field basically zeroed out in what we call the Lechamp anomaly for a millennium or so. And when it did, the cosmic rays came screaming into the Earth system, and you see in basically all sedimentary records this peak in cosmic ray-produced nuclides. We had a big cosmic ray signal, and the climate ignores it. And it's just about that simple. These cosmic rays didn't do enough that you can see it. So it's a fine-tuning knob at best for this picture. Okay? Space dust, it just doesn't seem to have changed over time, and there isn't very much of it. Okay? So now, okay, so now I got to get done here because we're going to run out of time real fast. But now let's do a little bit about climate sensitivity. CO2 matters to temperature. We can't find anything else to explain what happened. How big are the changes? Okay, what's going on here? The models actually do pretty well when you compare them to the past, which means that sort of the mid-range isn't bad. Now, there's cheating on the ice age cycle because you have to get half of the cooling from the ice sheets being reflective. You have to put the ice sheets in, but you really need the CO2 to get the ice sheets. And so the sensitivity to CO2 on the glacial interglacial cycling is probably a bit higher than the models have in them. The sensitivity, it's really hard to get the poles warm enough with modern models, so there's maybe a little more sensitivity to CO2 in the real world there too. This is a very interesting experiment. We have this thermostat of rock weathering, If CO2 didn't make it warmer, then when there's more volcanoes, the CO2 would just stay in the air and we'd have indications of huge amounts of CO2. And so this is work by Royer et al. It's a very interesting thing. So that sort of running through the middle here is the history of CO2. The green curve is the history of CO2 if climate sensitivity were huge, 6 degrees Celsius for doubled CO2. And the red curve is the CO2 history if it was only 1.5 degrees Celsius for doubled CO2. If CO2 doesn't warm much, when the volcano puts out more CO2, it just stays there, and there were times that there were lots more volcanoes, so there should have been immense amounts of CO2, but there weren't. And this also shows us, in fact, the best fit here is 2.8 Celsius for doubled CO2, which sort of looks like IPCC numbers. Okay? So what we find is that sort of, you could find somewhere in the literature people saying, oh, you get less than 1 Celsius for doubling CO2, and you might get up to 12 Celsius. Paleoclimate says, nah, cut off the ends. The middle looks really good, except on ice age cycling and for warm poles, the world is a little more sensitive to CO2 than the models it looks like. Okay. So where do we end up? We're gonna get out of here in a hurry. If higher CO2 warms, the Earth's climate history makes sense. And if CO2 doesn't warm, we have to explain why the physicists are stupid, and we also have no way to explain what happened. And it's really that simple, okay? We don't have any plausible alternative to that at this point. And so it surely looks like it, CO2 can be a forcing, it can be a feedback. The warming effect of a CO2 molecule, it does not remember why it's there. It only remembers that it is there. And the paleoclimate data show that sort of the mid-range models are right. And if there's a problem, the world is a little more sensitive to CO2 on some time scales than the models tend to produce. Okay. Now, be clear, there's lots of knobs that control the climate. The sun knob, we're really lucky it doesn't get twiddled very much. The cosmic ray, the space dot, the magnetic field, and the other knobs, if they matter, we can't find it yet. They're really interesting things to be learned, and I hope that the science rolls forward on those. But so far, they're either not doing anything or they're not doing much. They're fine-tuning knobs is how it looks. Okay? This is not a regional story. All right? You close the Isthmus of Panama, and the people that used to have coastal property don't anymore. They're climate changed. You take India from the pole and you run it to the equator, it's climate changes, okay? The Younger Dryas was a big regional thing. There's lots of things in regional climate that don't do much to the globe. The Younger Dryas is cold in the north, it's warm in the south, it doesn't do much to the global temperature. In terms of the things that people care about, CO2 is just a start, it's not the end. There are real interesting things to be done in here, okay? And I think there's a lot more work that needs to be done here yet, because where we really stand now, we're not quite yet at the pound on the table, this is nailed, we're done, this is our confidence interval level. The paleoclimate data are coming in real fast, they're real good, it's really sharp, but sort of these latest advances have not had time to percolate through to the IPCC yet. And so we're going to see more on this. We're going to see more discussion on this. This story is very clearly not done. Okay? But it's fairly clear where we stand now, which would be an increasing body of science, indicates CO2 has been the most important controller on the global average climate of the Earth. And so I thank you so much for inviting me, and I hope we can take a few questions, and thank you.
Thank you very much, and we do have time for some questions.
Yes. There's one back in the middle here. Yes, please. Right. So if the question was, if we burn all the fossil fuels, where do we get to? And there's this huge gap between sort of proven reserves and what we think is probably out there if we're really clever and really desperate. And so do we get it out of the oil shales? Do we get it? And people are kicking around numbers like 5,000 or 6,000 gigatons, I think is the number. There's a big number that's floating around on what might be recoverable. And if you take all of that and you turn it to CO2 pretty fast, there's some chance of getting above that Cretaceous level. And like I say, that was now, the temperatures may have been a little high at that site because the Atlantic is a little narrower and so the ocean circulation has slowed a little bit, but that was 37, 38 sea surface temperature. That was hot. So, so you know, you start thinking about this and saying, well, you know, if we really crank it up, are we really confident we're topping at 2 or 3 or 4 or 5 or 6 or 7 or, you know, you can think of a burn-it-all future getting really hot. Yeah, yes, please.
Here? There was one right here.
The question was that an Antarctic ice core or an Arctic ice core? The CO2 record I showed was for the ice core was an Antarctic one. The Arctic ones, there's a lot of work going on now in the hopes that we'll get good records out of Greenland. The records so far from Greenland tend to be pretty good, but they're blipped a little bit by the melt layers, and there's certain places where there seems to have been just enough carbonate dust and just enough acid that you get a little extra CO2, or you get a little CO2 reacting with the dust. And so things are a little noisy in Greenland, but there's hope that the North Greenland cores will actually give good records. For now, the CO2 record is an Antarctic record, and just stay with that.
Let me ask, I'd like to ask a question. We know that if we stop putting CO2 into the atmosphere, mitigation, that will stop, slow down global warming. But does geology teach us that there's any way to take the CO2 out of the atmosphere?
Yeah. So yeah, this is a great question, and it seems. I don't think there's any doubt that the weatherability of the rocks matters. And so, so we've got a pretty good idea that some of what happened with the great dying at the end of the Permian is that you have this immense amount of new rock which is breaking down like crazy to fertilize the ocean. And so that rock is really weatherable. It's just fresh. It's sitting there just waiting, break me down. I love it. And so anything that would increase the weatherability of rocks. The question is really one of economics. Can you make it go fast enough at an energetically low enough cost? If you could dig up an ophiolite, an old seafloor, and grind it up into really fine powder and spray a little water on it and let the CO2 react with it, the CO2 will turn into carbonate and go away. But how much energy did it take to dig it up and grind it into really fine powder? And so there are good people working on these questions so far, and there's also really good people, including Klaus Lagner, I think, has a display in the vendors, who are looking at the question of can we pull the CO2 out of CO2. People have looked at can we react to CO2 with carbonates, you know, dig up shells from on land rather than letting it do the job in the ocean and the coral reefs. So there's a lot of possibilities. None of it's looking real easy yet. And there's optimism, but yeah, none of it's looking real easy yet. It's, so I encourage you to check Klaus's stuff because that is indeed interesting. But it's probably still easier to keep it out of the air than to take it out with what we have right now. But right, so is there a relation of ocean acidity in relation to atmospheric CO2? For the glacial interglacial cycles, essentially there is, because the work of Berbel Honish and others using the boron isotopes, and now the work of Tripodi and others using the boron-calcium ratios, both reconstruct the Vostok CO2. And so we know what the CO2, so what they're doing is they're saying the ocean's pH is controlled by the CO2. But essentially, by doing the same time and the same resolution, they're checking whether that works, and it does. And so what you find is that the changes in the boron, which are a measure of the pH of the ocean, indicate a CO2 which very closely tracks the CO2 that was measured in the ice cores. There's a lot of work, there's a lot of ferment in the boron isotope community and the boron calcium community at this point. I'm sure we're going to see more refinements, but right now the sort of basic idea that ocean pH is tracking CO2 and looks very good. It looks very solid, and the few places that you feel most comfortable checking it, it works. Okay. So I believe that if I understood, and stop me, the question is basically about the feedbacks on the CO2. Now we're putting CO2 up and roughly half is going into the ocean. The expectation is as we get more CO2 up, the ability of the ocean to buffer that goes down a little bit. And so, you know, the fraction that remains airborne increases with time. And then there is this probably a pretty good idea that longer term, decades, centuries to a small number of millennia, in a warmer world that you may pull CO2 out of places that it's hidden now. And the biggest concerns would be the Arctic soils, other soils, if you make the Arctic soils more tropical. There's a huge complexity, but the knee-jerk response, which may be accurate, is that they lose their CO2 because they're getting more like other soils that have less CO2. There's a whole lot of carbon as methane in the seafloor. If you make it warmer, that comes out as methane. It becomes CO2. And so there's a lot of these reasons why you have a suspicion that as you go from decades to centuries or a small number of millennia, the sensitivity to CO2 that we put up actually goes up. And so rather than being 3 degrees warming from us doubling CO2, it might be more than that.
One more question, Paul? No? Okay, well, thank you very much.
Thank you.
Thank you.